Welcome dear students. Today we are talking about the second lecture. In the last lecture we have initiated the learning about the new kind of materials, superconductors. We have started with electrical conduction in materials and classification of materials on the basis of electrical conduction. And finally we concluded with a new kind of materials called superconductors. In this lecture, we will discuss about this phenomena, from where this phenomena came into picture, who developed this, what is the significance of this phenomena, what are the properties related with this phenomena that can be used for future applications also. We will discuss in detail about superconducting properties. In this lecture, first we will discuss about learning outcome, the student effective learning outcome. Then we will move to superconductors, the properties of superconductors, the interesting features about this, the feature of magnetic field expulsion or the disappearance of resistance, and finally we will discuss how a lot of work has been done in the last 100 years and how we move from 4 Kelvin to 200 Kelvin. Various example we will discuss. Finally, exercise and references. We will learn about new kind of materials, superconductors, and characteristics of superconductors, and brief history about that. We have introduced this the concept of SELO, student effective learning outcome, and we must know this. Then, if you learn this chapter, the chapters of superconductors, then this will also help you to solve problems. You can think of about the applications of superconductors. You can think how to use these superconductors in various places and how some unresolved issues can be resolved about the superconductors. So I'm using this SELO1. There is a list that we are using and provided by our university. So this falls in SELO1. The superconductive phenomena was first discovered by Dutch physicist Kamerlingh Onnes in 1911. This phenomena is a quantum mechanical mystery, as ferromagnetism and diamagnetism we studied. It has significant in the way that this opened a lot of studies. Kamerlingh Onnes was studying the materials at low temperature and got this results suddenly. Just to keep you more awakening, you must know it's a fun. He is the person who got this prize, this Nobel Prize alone. No, this was not shared by anyone. He was working on the materials at low temperature. He got the prize for investigation on the properties of materials at low temperature. And he worked on production of liquid helium. That is very important for us. But the results were very interesting, very shocking, and had a lot of potential to develop in future. That we have seen from the 1913 to this year. Lot of work had been done in this field in the last 107 years. Basically, he was working on cryogenics techniques. The basic objective of that work was to get something for cooling. They wanted to work at lower temperature, and for that they tried to liquefy the helium. Now what they observed when different substances are cooled to very low temperature, the properties may change. He started work on cooling of helium to liquid form. Fluid helium was carefully studied and become an important aid for the cooling of different substances and charting the properties of lower temperature. The property change is really interesting at this small temperature, and especially the electrical change. We use the word super V's, super why? Because the property is not only changing but drastically changing. He started this work in 1908, and in 1911 he discovered that the electrical resistance of mercury completely disappeared at a temperature which is near to 4 Kelvin, which is just about absolute zero. This phenomena is known as superconductivity. The materials that give this phenomena called superconductors. As a common practice, the term super is used for extraordinary properties. Superman, extraordinary. Yes, here the conductivity is extraordinary, infinite, no resistance, resistance disappeared. So that is very important in this point of view. It is always interesting as a physicist that most of the, or you can say many discoveries done by accidentally. He was not the person who was thinking anything about disappearance of conduction. He was thinking about cooling at lower temperature. He was trying to prepare something that can be used to cool others. Such type of arrangements are called cryogenics. He was studying the resistance of solid mercury at cryogenic temperatures using recently discovered liquid helium. He was using liquid helium as a refrigerant here there. But what he observed that at that temperature of 4.2 Kelvin, the resistance abruptly disappeared. In subsequent decades, the superconductivity was found many in many other materials, in metals, then in alloys, binary, ternary, quaternary, and now we are also thinking about some carbon-based materials. So it has opened a lot of applications. But why? We will discuss the other slides. Superconductivity is a very exciting and unusual macroscopic quantum phenomenon. Different superconducting devices are continuing to find more and more application around the world. I am sure in the future these applications will become more widespread. But if you are interested in this, that is the appearance of conduction, then how it can be used in applications, and same the magnetic behavior, how it can be used for the some materials, because there is sudden change in the magnetic behavior also. For using this, we have to know the general aspects of superconductivity. Superconductivity is the set of physical properties that observed in certain materials where electrical resistance vanish. Yes, zero electrical resistance, and at the same time the magnetic flux fields are expelled from the materials. These are the two important properties that associated with superconductors, and these properties make superconductor very special. When you reduce the temperature of those certain materials at particular temperature, that is called transition, the electrical resistance vanish. At the same time, there is another feature, that is magnetic field lines suppose passing through that material, but when you reduce to that critical temperature, the magnetic field lines expelled from the materials. So these two factors were generally very important things for all. We have many queries with this, because yes, if you have zero resistance, it means whatever your current you are having, it will be continue to be there. There is no loss of current with this. And of course, in the time when we are facing too many energy crisis, it looks very fascinating that you are having something where current will not be decreased. There is no loss of current. But then the question is, why, if it is so good, then why we are not using nowadays? This is the challenge on that side, the challenge of room temperature. You can't achieve, even today, we can't achieve this at room temperature, the 107 years. This is possible only at lower temperature. Of course, too many work have been done, and people are working to increase this temperature. Still, temperature is very low than room. At the same time, this magnetic flux expulsion may also be used in many applications. This effect, also termed as leviation effect, and Japanese are using this concept for running trains, maglev trains they are using. There is no resistance there, Many applications may be developed, but the one limitation that we are facing is room temperature existence is not possible till today. Those are working on this. The concluding remark for this superconductors, the superiority of superconductor is, unlike a metallic conductor whose resistance decreases gradually as we reduce the temperature, a superconductor has characteristic critical temperature below which resistance drop abruptly to zero. This is not possible with normal conductors. An electrical current through a loop of superconducting wire can persist indefinitely with no power source. If you have a superconducting wire and you create the current, then it can be used for up to the age of this earth because there is no loss will be there. The resistance of a normal metal gradually decreases as the temperature is lower. The resistance at absolute zero is determined by electrons scattered by impurities. Because now electrons is passing through the absolute zero, but at that time everything is frozen. Now electron has some resistance. This is due to impurities or defects in metals. And that is why we always say then size and shape, structure also played a very important role in resistance and conduction behavior. We have already discussed this and just revising again. The resistivity is continuously decreasing here in both the cases, whether it is a metal or superconductor. But here there is no line after this critical temperature, and this is transition temperature is called. After this there is no resistance, but metal always have resistance even after at lower temperature. So this is the basic difference between the metals and superconductors. After the discovery of this temperature of helium, liquid helium, which is at 4.2, you can say it is also having a boiling point of 4.2 K. Many other materials also studied, and some typicals are 9.25 for niobium, 7.2 for lead, and 1.1 for aluminum. Forget about 1.1, but take these 9.25 and 7.2. We were trying to increase the temperature till since 1911. Then it has also been suggested that superconducting materials can be also be created in under pressure, high pressure. Some noble metals like copper, gold, silver have not been found to undergo a superconducting transition for temperature as we reduce this. So these are certain interesting factors. Some materials are giving superconductors, some are not. The transition is different for different things. Since then, what is we got until 1986? The highest known temperature ever is 23.24 NB3GE. This is the highest up to 1986. But after this 1986, this field got a boom, and many scientists, researchers started work on this to increase the room temperature. In this slide, some superconducting transition temperature and critical magnetic fields for some materials are shown here. The critical magnetic fields are the field at that temperature. It is also termed as HC. For aluminium, as we have discussed in the last slide, the transition temperature is 1.1. Then for tin, 3.7, lead 7.2, and so on. You can get this here. So highest temperature is niobium 9.25. That is the reason a lot of work has been, people have been done on this. But even then, with some compounds, they fail to reach for higher temperature. Only they move from this 9 Kelvin to 20-25 Kelvin. In 1986, the highest TC for superconductors was about 23.2, but within a year, people reported TC at more than 120K. And they tried to a new version, new direction of these superconductors and high pressure areas. This started a new period of high research activity in high TC superconductors. But till today, even after a lot of things have been done, they have not received the superconductor at room temperature. If we can receive the superconductor at room temperature, then that may be the one of the best thing for us for many applications. But till now, nothing appreciable we have in our hand. In the given slide, I have just shown how the development took place in the last 20 years. How we move from metals to other fields. In 1900, we started with mercury, then continuously we are moving in the top direction here. From 4 to here we have reached to 40 in 86. Then from there, from 1990, sudden we have moved to this to 50 here, and however some results are here also at 150, and finally up to this year we have reached to 200, roughly 200. But even if we are below room temperature, so that is very interesting journey. Scientists are working on this ternary, quaternary alloys and everything, trying to get the things. Interestingly, FES is also giving here these results. So it is very interesting to show results. This is also a very interesting consequence. One we had discussed with temperature. If we reduce the temperature, then suddenly resistance disappears. But in this case, in these materials, suppose you are having a ring of that superconducting material and you keep that material in magnetic field, and when you reduce the temperature, then suddenly all the lines will expel from the ring at lower temperature than Tc. Now the current that trapped here, you are observing this, is trapping here. Water is trapped here. There is no reason to loss after this. And that is why that this will persistent indefinitely all the time without decaying. On the other hand, the current carrying capacity of superconductor is finite and cannot exceed a critical current density, above which it revert back to normal. So there are certain restrictions, but the phenomena that we are observing are very interesting to know. In the coming lectures, first we will talk about many interesting properties of superconductor behavior. Then we will also discuss what are the cause of this. BCS theory is one of the most important theory in superconductors, which was given by Bardeen, Cooper and Schuffer, that explained that superconductivity is caused by electron lattice interaction, and the superconducting electrons consist of a pair that called Cooper pair. Electrons form Cooper pair in these. This all happened at lower temperature. So we will discuss many other interesting things and facts in this unit. Let alone. The exercise for this lecture is try to make possible applications, a list of possible applications of superconductors that you suggest, that you feel is superconductor can be used in these places. However, we will discuss these things later in the classes, but try to work out. I have discussed two properties here: the expulsion of magnetic field and disappearance of resistance. Can you suggest some applications? Another exercise I'm giving here a list. Prepare a list of superconducting materials that have finite chances to achieve high Tc in future, because the achievement of higher transition temperature is still a dream. These are the books for reference. You can use these books: Introduction to Solid State Physics by Kittel, Solid State Physics, Estrop and Mermin, also notes by M.S. Roslos. Thank you. In the next lecture, we will discuss various properties.